Thank you. Yeah, so I would like to this is tutorial, but this is also, I would like to bring together some ideas which are somehow quite classical, but also, things have really changed in machine learning in the last, so many years. I think it's pretty obvious. And there have been changes in how we understand generalization and changes how we understand optimization. Particularly for generalization, this has been a a somewhat, I might say, kind of shocking development that things which we thought could probably not work, or certainly not work that well, turned out to be amazingly good and exhibit this stunning capabilities of understanding and generation and all sorts of things, which were way beyond any expectation that we had. And so the theoretical aspects of that we've been trying to understand it, and I would like to point out some classical analysis of this and show what changed and what is it that we don't understand, and in particular discuss some very recent developments in phenomena such as emergence. So this is basically going to be two questions here, and you can think of very simply two questions in the theory of machine learning. The first one is the question of generalization, and in the simplest you can think, well, why do neural networks, or other methods as well, but in particular, obviously, like everybody wants to know about neural networks, why do they generalize to unseen data? The second question is the question of optimization. Why can non-convex objective functions be optimized? It turned out that the first question is rather mysterious. The second question turned out to be actually much simpler than we thought it was. We have a fairly satisfactory idea of how this optimization works. Not maybe the details, but at least in general. The first question is I'll discuss. We have actually made a lot of progress, but we don't have a very good understanding what kind of skills that things can learn, or how generalization happens, and why they generalize. And this is even true. I'm not even talking about LLMs. I will talk about much simpler models than that. And even those are fairly strange. Okay, so first, what is generalization? And let me maybe just give by the way, feel free to interrupt. I mean, this is supposed to be a tutorial, and I'm more than happy to stop and discuss any questions that you might have. There is no reason for me to rush ahead. So first, what is generalization? And maybe the very basic of generalization is really what you want to predict. Some future from the past. And maybe if you want to take some evolutionary point of view on this, you can maybe think of it, okay, it's a filter in non-generalizable properties of, say, organisms just don't survive in the evolution, right? If you cannot figure out, you need to figure out where to get food, right? If you don't get food, right? If you don't know how to get food in a consistent way, right? You don't survive. So that's a very simple maybe basic. And I starting to suspect that maybe a lot of properties that we think of generalization are really stem from this. But let's discuss maybe more specifically in machine learning. So what do we mean by generalization in machine learning? Let me set up the mathematical framework for this. And so I'll consider a very simple setting in machine learning, but simple, but it's fairly general. So you have some input data, xi. Maybe xi are the pixel values of your images, and yi's are, labels, cats and dogs. Everybody likes those animals. So +1 and -1. So now, given a bunch of images of cancer dogs, you would like to make a prediction which image is a cat and which image is a dog, right? That's a very basic problem. If you think about it, in fact, majority of machine learning models really is set up this way. And even most things that we think of generative models, like when we think that, okay, ChatGPT is a quote-unquote generative model, but if you think what generative model really means, it actually just predicts the next word. So you can think of ChatGPT doing exactly this, right? Then the way you use it, of course, is slightly different. Yeah?
I think there should be some pushback on that, though, because it's not doing classification. It's really trying to get the distribution over the next token. It's not selecting a particular
I actually disagree with this, because you can switch off. If you turn the temperature to 0, it becomes fully deterministic. It's just predicting the next token, and it still works fine.
Yeah, but that's not how it's trained.
No. Training is separate. I'm talking, you want to have, you're given this, so think about training as a black box. You're given a bunch of examples, and you want to have a machine which predicts the next, whatever, the label of the given example. And that's exactly what ChatGPT does. Okay, if you turn the temperature to 0, that's exactly what it does. And at temperature 0, it still works fine. So yes, you can say that in practice it does something slightly different, but it's not very far from this. Yeah?
You're right, the images are not 0, negative 1, 1.
What's that?
Your f sub x goes to r, but the y's are negative 1, 1.
Oh, 1, these are real numbers, right? You can more generally, of course, look at regression, but you can view this as a very simple case of regression, right? Just 1 and minus 1. Okay, so now, okay, I'm not claiming this describes all of modern machine learning, but it's not too far from what a lot of very complex systems actually do.
How does it differ from any other mapping? Because this is a subset of all sorts of mapping from certain input to certain output.
Yeah, exactly. It's like, this is a crazy problem because like, you think like, okay, given this finite set of points, now find me a function which fits this point. Like if you actually think about it, it's like completely insane. So what is that we, right? Like clearly we need something more. We cannot just say that. It's extremely underdetermined. I'll say something about this because this is, we have some sort of what's known as an inductive bias. So we definitely have preferences for certain functions that fit data, right, over others. Because if you just say, okay, well, there are infinitely many functions which fit this data, right? Just choose one, it's not going to do anything. So that's the kind of key in generalization, right? Because in principle, you have this infinite space. But you have to somehow have some idea which part of this infinite space are, quote unquote, reasonable and which are not. Yeah?
When you say we have preferences, do you mean we, like mathematicians, through experience, have preferences? Or is there another reason for the preferences?
Well, not just that. I think it's much more basic than this. Like imagine like you're a single cell organism, right? And you have to figure out where the food is, or like, how to avoid, the bigger single cell predator which wants to eat you. You have like, in principle, you have like infinitely many strategies, but you actually definitely have like there is some sort of idea that certain strategies will like lead to you surviving and some will not, right? So that it's some sort of nature, right, that gives us. It is some sort of regularity, but what kind of? Well, we have various, like we have various sort of kinds of knowledge about this, right? If I measure temperature in this room, I can be pretty sure that my measurement here and my measurement there are probably pretty similar, right? If I start measuring temperature, like outside, maybe it's quite different. So we do know a lot of, we know that if you have a cat and you change 1 pixel, of an image of a cat, it's very likely to still be a cat, right? Some sort of continuity or smoothness or Lipschitz condition, whatever you would call that. Yeah?
You sometimes talk about the temperature. This is parameter in the updating. How?
Well, if you imagine, like, I just want to predict temperature in a room, right? And my x in this case is just coordinate of the room.
When you were responding to the question, as before you said.
Oh, temperature. I'm sorry. That temperature is completely different from this temperature. This is basically when you sample from this model, temperature is also how. So it gives you potentially many predictions, and depending on the temperature, is how deterministic you are selecting from those predictions. So low temperature would be very deterministic. High temperature will be very random.
Temperature 1 would be like sampling from the true distribution. Temperature 0 would be take the most likely.
Most likely, yeah. So it predicts some distribution, and you can just take the most likely, or you can like sample from that. Okay. So now, so basically what we want is the following, and this is maybe very strange ask, right? We want to have a function f. So imagine there is some sort of true function. Okay, this is some sort of simplification, but we can think there is some sort of optimal function, like there is some underlying ground truth. And we would like to construct or deduce somehow this function fx from the data, which is somehow approximate this ground truth. And even for an organism, there is probably some sort of best behavior. We can think maybe usefully that there is some best behavior. You go left or you go right. You go right, you eat. You go left, you get eaten. Something like that. So now, what is this true function, right? This is some sort of expected value over the data which we haven't seen. So this is predicting the future. And of course, we don't really have access to this at all in general. So we want to have the most accurate classifier for dogs and cats, which will be shown to us in the future. Now, in this formulation, this is far too flexible, right? Because I didn't tell you anything about this distribution. I didn't tell you anything about all these functions, so you cannot really do it. So let's think about how we can think about this. And the way almost all current algorithms work is by what you may call algorithmic empirical risk minimization. And basically, you construct some sort of a loss function, and you try to minimize it by some algorithm. In practice, this is usually a version of gradient descent. So very simple greedy algorithm. Now, what is the empirical risk? You have xi and yi, and you construct some sort of loss function, how well your f predicts y, right? So the simplest one is maybe you can just take the difference, well, squared usually, the square loss. And notice that I'm using some sort of loss function which may not be the same loss function as you actually want to see in the future. Because in the future, you want to be most accurate at classifying cats and dogs. But that's a binary function, right? It's 1 if you classify it correctly, 0 which classified it incorrectly. That's not the function you can optimize in practice. So maybe instead of this, you're using some sort of square loss, which is something you can differentiate and do gradient descent on. So that's basically how it works. So you can think you minimize empirical risk of a class of functions using some algorithm A. And in general, this train and test are not the same. In practice, you use something like cross entropy or square loss for training, typically. Okay, so that's empirical risk minimization, algorithmic empirical risk minimization. I'm emphasizing that aspect. Now, so the key question is, well, when is whatever that algorithm gives somehow close to this ideal distribution or ideal prediction? And specifically, what are the practical problems that we're dealing with? Well, how do you select model architectures and parameters, right? Like, well, if you have a neural network, how many parameters do you want? That's a choice. Second, which is actually equally important, especially now, like you usually train these things using some form of gradient descent. This gradient descent is an iterative procedure, right? You just run it. How long do you run it? So you need some notion of measuring progress, right? If you don't make any more progress, you stop. This is what's known as early stopping. Well, turns out these are very tricky questions both, but this you can think of both as measures of generalization. Okay, now the great simplification is the following. First, let us assume, so this is for theoretical purposes, because obviously if we don't assume anything about the future, like we cannot say anything. Yeah, question.
This question is kind of inspired by all the other talks as well. So you said the loss function, you would pick something kind of smooth. What if there was some glitch in learning and that would cause for example, the loss function to become not smooth? Does that ever happen in practice?
We don't have such things because these are all mathematically constructed, right? So it's not like a biological learning when you can imagine there are okay, you can imagine maybe there is a glitch in a computer and so on, but we don't usually think like what happens if there is something wrong with the computer.
Could there be types of glitches that would strengthen the learning though?
What do you mean by glitch?
Discontinuity or just like a sudden change in the loss function because it would improve the loss. The differences between fxi and yi, for example. I don't know.
We don't usually deal with those things because we set everything in advance and then just it's a mathematical process. So we don't have that kind of setup.
It's contrived, so that doesn't happen. I understand that.
Yeah.
Maybe just to contribute a bit to that is, even though we do construct this mathematical form which is smooth, you could still have a difference in like the null space of the Fisher information matrix or something like that when you get like genuinely different solutions as you cross through weight space.
I will discuss genuinely different solution, but that's a slightly separate issue from, that's actually a really important point. I'll talk about it. So you can have, so just choosing the loss function is somehow not quite the whole story. But you don't usually change the loss function. I think in this sense it's fundamentally different from biology because biology is like whatever happens, like like you get these processes which kind of happen naturally. Here, everything is set up by us, so we have full control. Which is actually, in my mind, this is really nice because we have full control. Nice or maybe sad, right? Even we have full control, we still don't understand what's going on. Like this is just, LLMs are just mathematical formulas, right? It's just big matrix multiplication. That's all there is to it, right? Like we know matrices. Yet we don't understand what they do. Biology, of course, is much more complex. Okay, so in any case, this is a great simplification. So training and data set, we assume they have the same distribution. That's number one. Number two is train and test a sample IID. Now, there are a lot of questions why this is a reasonable simplification. I'm not actually even going to go there. A little bit about same distribution I'll talk about a little bit later. But the point is, this is the most basic setup. If we cannot understand this setup, I don't think we can make progress on anything else, right? Like this. We should definitely be able to make progress on this. Yeah.
Any work on modeling it not as a random variable but as some other sort of process? Maybe there's a program generating the data.
Yeah, there are all sorts of extensions of this, but my point is that this is the kind of very basic setup, right? This is probably the simplest thing we can come up with. Like we don't want to start with something even more like if we cannot solve this, right? Like hard to imagine how much progress we're going to make overall. Okay, there are a lot of caveats to this, but yeah. Yeah.
I think if the constraint of being from the same distribution, I think it's sufficient, but I wonder if it's necessary. Because we do all sorts of generalizations where I learn arithmetic on integers and I can generalize it to all sorts of other numbers.
I'll talk actually exactly about
Okay,
this.
great.
So it's definitely too strong. Like, I am not saying this is a really model for what happens. Like, clearly nothing is quite from the same distribution, and nothing is really ID in real life. But we need to start at some sort of mathematical abstraction that we can deal with. Yeah.
So I have maybe a clarification question. So in this case, the meaning of the same distribution kind of is the same as kind of one of the I in this ID, like identical, or like the.
Yeah. So imagine like you have a self-driving car, and you're saying, okay, we have like images, and these images are sampled like uniformly at random from distribution, and in the future it will encounter exactly the same condition as before. Clearly it's not realistic. It's not going to be exactly the same. But maybe it's not bad as a start. Okay, well, if it is the same, can we say something reasonable, right? That's okay. In any case, my point is that even in this case, it's really tricky. Like, this is a very simple case. Turns out this is tricky. And here's what I'm going to talk about. Well, first I'll discuss how like some classical analysis work. And so how do people think about generalization? Like, first I'll discuss this kind of WYSIWYG. What you see is what you get bounds. And then it turns out, oh, well, it doesn't quite work in practice. And then I'll discuss this kind of interpolation and what happens with phenomena like double descent. And you can say for those things, the training, so in this classical analysis, almost all of them, with a couple of very special exceptions, training loss is basically the same as a test loss, which is great, right? Because you train something, you get a loss, and that's predictive of what you will get. Very satisfactory. Turns out doesn't really work. Oh, at least doesn't really work in a lot of really interesting, important cases. So it turns out training loss is not predictive, but validation loss is still predictive. Maybe. And the phenomenon of emergence, actually, which we started to understand only very recently, is that even the training loss is not predictive of itself, and that's a serious issue. Validation, sorry, did I say training? Yeah, thank you. Validation or test loss are not. So test loss is not, so when you train something, the test loss at iteration like 10 is not predictive of the test loss at iteration 11. That's really bad because you don't actually know. Like imagine you're OpenAI, you're training some model, like how do you know that you shouldn't train it for like 2 more hours or something? Maybe it will develop some amazing capability or some terrible capability, who knows? Okay, and finally I'll talk about optimization given time. I'm more, I think the generalization is really the more maybe important part of this talk. Although optimization is nice because we can kind of understand what's going on. Okay, now, so here are some classical analysis. And a lot of recent work has been sort of concentrating on empirical risk minimization or structural risk minimization, this ERM, SRM theory of learning, which tries to bound some sort of complexity of the function class. And then there are other ways, very classical. Well, some of them is basically like things like even like regularized linear regression or some sort of non-parametric methods like splines. Yeah, there are other methods like nearest neighbors, Nadarai, Watson. Almost all of the things result in what you may call WYSIWYG type of analysis. So the test loss and the train loss are effectively the same. So what kind of, how does it work? I'll just discuss ERM theory, but you get something similar with most other analysis. Okay, so remember goal of machine learning, or goal of generalization, right? Our goal is to have some sort of minimum of args, to find F, which is minimizes some sort of loss over the unseen data. And the goal of optimization itself, that I call just ERM, but this is really optimization, is to minimize the loss over the training data over some class of functions. Now, I'm actually not separating this loss. I'm just assuming for that's another simplification. I'm assuming it's the same loss. Okay? Now, Vapnik, in his famous work, he said that the theory of induction, that's what he called generalization, is based on the uniform law of large numbers, and effective methods of inference must include capacity control. So uniform law of large numbers and capacity control. Now, uniform law of large numbers in this context says that basically if your function class, your candidate class, this H, is small enough, you can say that for every element in this class, for every function in this class, the expected loss is close to the empirical loss, which is effectively just the law of large numbers, right? The law of large numbers says that the average, like if you toss a coin, right, the average is close to the expected value. And you want the same thing, but over a class of functions. And capacity control is basically saying, well, how many functions do we need, or how large a function class needs to be to make sure that we have some functions in this class which are, you know, like reasonable approximation of the ground truth. So that's his theory. And the kind of underlying bound for this is the following. You have the expected risk, which is what you get. And you have the empirical risk, which is what you see, right? And the bound says that the expected risk is bounded by empirical risk plus a term which depends on some notion of capacity of the class. I'm not going to define the things, and there are like many different ways to measure capacity, sort of the most classical probably being VC dimension, which Vapnik and Chervanyankis introduced. VC stands for Vapnik, Chervanyankis. So this is, there are other forms of this, but this is roughly what this bounds look like. Now there's N is the number of data points here, and C is some sort of measure of capacity of the class, some sort of dimension. Now you can kind of see that if N is significantly larger than C, this is going to be small. And these two things are going to be approximately the same. So that was the idea, and this is a very sort of classical idea. This is from Vapnik's book. As you increase the capacity, so this H corresponds to that C that I had before. So as you increase the capacity, well, your ability to model increases, but the class also increases, so the bound becomes less tight. So you need to balance somehow the C and N. So basically, you have to choose the capacity to be significantly smaller than N. And this corresponds to this, like altogether, you have them sort of, this bound gives you a U-shaped curve, sometimes known as bias variance trade-off. And you want somehow to be in the middle where the bias and variance are balanced. Okay? So that was his sort of, oh, no, not just his, this was kind of received wisdom. Yeah?
The problem of increasing the capacities is related to overfitting?
Yes, so if you increase capacity too much, you overfit. If the capacity is too low, you underfit, okay? So this is a kind of very basic setup. And, we believed in it for many years, until it turned out to be not quite correct. Yeah?
When Vapnik initially kind of defined this notion of or when your colleague defined this notion of complexity, was he talking about the complexity just of the model or hypothesis space, or was he talking about that including also for, like, in his mind, was he also thinking about like the distribution, the algorithm as well, right?
No distribution. This classical bounds are distribution independent. Later, there were like distribution-dependent versions of this. And you can also talk about capacity of a class, or you can talk about complexity of a function itself. But in this case, this is just capacity of a class. And it's given by some maybe covering number or VC dimension, this type of object. There are many, there are probably like 20 different ways you can do this. Rademacher complexity. Okay, so now the question is, well, is WYSIWYG necessary? And we're sort of, it has been sort of taken as a sort of article of faith that fitting data exactly was a bad idea. And, you know, like, for example, here it says, like, the estimate on the right seems to be more reasonable than the estimate on the left. Why? Because that fits the data exactly, interpolates the data. So when I say interpolate, this is what I mean, right? It like literally just fits the data exactly. Classical mathematical interpolation. Now, this is a WYSIWYG, right? This is not WYSIWYG because on your data you have zero loss. It fits them exactly. But probably off your data, it's not going to fit exactly, unless you're somehow very lucky. Yeah?
So what you see is what you get is WYSIWYG, right?
Yes.
So can you explain what you mean by that?
What you see is what you observe on your training data. What you get is the future that you don't see. So like, you know, you cannot, for self-driving cars, like what you see is, you know, your training. They said what, you know, is it going to be the same as what you get in the future? Well, if you go to a different city, it's probably to not be quite the same. I mean, ideally, generalization, of course, should adapt to new environments as well. Same thing here, you know, like a model with zero training error is overfit and it's bad. But now, is it really so? Well, let me give you kind of two examples that we have observed recently. This was, I guess, kind of the first observation in sort of modern setting of this. I'll point something out. Something like that actually had been observed well before that. What they did, they took a neural network of different widths, and they just trained it to get zero loss. And this is a test at convergence, and this is a test at some sort of optimal stopping time. And you can see that there is really convergence, meaning that you just interpolate the data. I mean, you cannot exactly interpolate, but you make it very close, the loss close to zero. And you can see it works just fine. Like there is not a lot of overfitting. So somehow fitting the data exactly doesn't look like it's such a bad thing. And even more famously, in this paper, Understanding Deep Learning Requires Rethinking Generalization, they did a bunch of these experiments when they showed that the training accuracy is 100%, so they fit the data exactly. This was on CFAR10, so it's an image data set. And they observed that the test accuracy is very good. Now, maybe it overfits, it's a little unclear, but if it overfits, it doesn't overfit by much, right? It's not bad. It's 90%. It's really doing quite fine. Okay, any questions about this? Yeah. This is a 10-class data set of images. So, and this is accuracy. So, percentage of wrong classification. Yeah?
Do you know in this case if the training loss was like log loss or something else?
This is almost certainly cross-entry. I didn't check, but it's almost certainly cross-entry. But you can get the same thing with a square loss. It doesn't make a big difference. Yeah?
Yeah. Does this depend on the size of data set? Because the toy example you showed, it's like 10 data points. So if you overfit, then it's obviously going to be quite dramatic. But if you're training with a real data set of like 10,000 points,
then it's going to be way less dramatic, I would imagine.
This is 50,000 data points, and the number of the parameters here is 1.5 million. So it's well over parameterized. And you can see it. Yeah, so it depends on the number of training points. Now, okay, well, yeah.
So was there any insight as to what caused this? What was different about the new data that was not covered? Or can
I'll discuss why something like that is actually not so unreasonable.
So I can cook up a toy example where the image quality is the same. For example, I train a model with right side up faces, and I show it upside down faces. And maybe at least human beings will fail miserably if they're to classify upside down faces. So the image quality is more or less the same in some ways, but I just did an angular transformation and the model failed completely.
Oh, this is the same. Test and train are the same, right? So this is a very limited. I'm not saying anything about generalization to a different domain like that.
I'm saying that while here interpolation in some sense seems to fail, one can come up with, at least for human beings, reasons why it fails. At least in the human example, one can see, if I create a toy example, I don't know if the image classifiers will also fail similarly, but that's one way to get an insight into why it doesn't fail.
Yeah. Let me continue because I'll have something. I'm not sure this will answer your question, but I think it might shed a little bit of light on what's going on here. But let me make it a little bit more dramatic. This example first. I'll show you a more carefully controlled example when something like that happens. Yeah.
Can you say how much of the data set was used for training and how much was...
This is standard one. This is 50,000, I think. I think it's 50,000 training and, if I remember correctly, 10,000 tests.
And are these randomly chosen, or is it...
Yeah, they're pretty much ID. I mean, whatever that means for actual images, but as close as it gets. This one I don't remember. I think it's probably similar. It's probably the same. Okay, let me now first point out some historical note, which I think is quite interesting. And this is from '98, and there's a paper on boosting, which provided this kind of margin bounds. And they point out that very, very similar phenomenon had been observed for boosting. The test error of the generated hypothesis does not increase as the size becomes very large and often is observed to decrease even after the training error reaches 0, right? Exactly the same thing. And this, like mid-90s kind of people had seen this. And I guess it didn't quite... Kind of surprising that we had to wait for like another 20 years to get to see how important this thing is. Okay.
I'm not understanding what it means for it to decrease after the training error reaches 0. When the training error is 0, why? What's the...
So the training error is 0 just means in this case you can continue boosting because the training error is measured differently. The training error is classification error, right? That's measured differently from. So you can train neural network, for example. Well, this is boosting, but you can train neural network even after your training error is 0 because you are measuring. There is a disconnect between the test loss and the train loss. The test loss stays a continuous thing, like cross entropy or square loss. The training loss, the test loss is accuracy, which is once it reaches 100%, it cannot get any better. But the test loss can still get smaller.
Is it more or less
the training loss, I'm sorry.
Is it more or less the difference between reporting the probability distribution as the output versus the actual maximum of that?
Well, it's not exactly the probability distribution, but one is continuous, one is discrete. You can continue to optimize a continuous thing even after discrete cannot move anymore. That's, yeah.
And maybe just another way to say this is that the training accuracy is not the loss on which you take the gradient.
That's why I made that distinction in the beginning. But let's see what happens, because you can actually bring them. That's why I want to show you the next thing, because this is an unnecessary complication. Yeah.
Oh, just really quickly, I can only say this for boosting, but it's actually it's a really interesting problem that's not actually fully understood yet. But I think the most viable things tend to sort of like that it's like maximizing the margin, right?
You can explain it in terms of maximizing the margin, and that's a really good explanation. But it's let me continue. Yeah, maximizing the margin has a lot to do with this. It doesn't quite explain this, but it's definitely the right way to think about it. That somehow when you train, you keep maximizing the margin, and maximizing the margin has some benefit in terms of this. Let me give you a very clean setup for this, which actually kind of gets rid of some of these complications. So how would you test model complexity? Well, the easiest thing, so suppose, you see the problem here, I don't know what the real error should be, right? So when I say WYSIWYG, I think what you see is what you get. Well, I don't really know what I get. What I see, of course, is 100%. But if it's 90%, and what I get is about 90%. Maybe if I just train a little bit better, I would get 100%, and it would be WYSIWYG at the end, right? This doesn't prove that this is not WYSIWYG. It suggests that it's kind of unlikely that you can predict these images perfectly, but it's not completely clear. So let me make a setup when you cannot get what you see is what you get, okay? So here is what I'm going to do. I'll just take, this as a cartoon, I'll do it with real data. But so I have some data, and suppose it's a perfectly clean data, right? And now I'm just making it artificially less clean. How do I do it? I just flip some labels of them, right? Now I know that, like, say, 10% of the red ones become blue and 10% of the blue become red. Now I know that my perfect prediction cannot have error which is smaller than 10% because, like these are random points and I cannot predict them. On the other hand, in training, I can obviously fit even the noise. Nothing prevents me from fitting the noise. So in this case, what you see is always going to be 0 because I'm just going to fit the noise. But what you get cannot be smaller than whatever percentage of noise I inject here. Okay, is this clear? So WYSIWYG definitely does not work. And if this overfitting sort of effect was bad, like you would expect overfitting to become very bad, right, as you're injecting noise. Because you're fitting noise, you're probably doing terrible stuff. So let's do it with the real data. And let me just explain to you the setup. So this is MNIST, which is this digit data set. So there are just 10 classes here. And you're predicting, from an image, you're predicting which digit it is. And it's close to being perfectly clean. You can get like 1% error or something like that. So you can say maybe it's like pretty much you get perfect prediction. But let's now inject noise to this. And so on the x-axis, I have this amount of noise that I inject. And on the y-axis, I have classification error. So when you like inject 50% of the noise, the best you can have is roughly 50%. Actually, it's a little less because sometimes by randomness you just get the right label. But you get something close to 50% error, right? This is a 10-class problem. So random prediction would give you 90% classification error. Perfect prediction will get 0. And you can see that as you inject more and more noise, you kind of just linearly interpolate between 0 and 90%. So no possible predictor can do better than this green line, right? That's optimal possible. Now, here is the surprising thing. If I just take this Laplace kernel, and I'll talk about kernels later, but right now it's not very important. You get very similar results with neural networks. And you fit it exactly to the data. And by exactly, I mean that the square loss is effectively 0. It's like 10 to the minus 25, okay? So this is like true interpolation. up to machine precision. You can see that even as I'm increasing the amount of noise to quite high levels, like 60% of my data. So I'm fitting 60% of like just garbage. And I'm still not too much worse than the best optimal. Okay, there is a little bit of negative effect, but very small. So overfitting really is not a big deal, right? Yeah.
This may be something that's in the paper, but do you have any, can you recollect what the ratio of kind of D to N is in this example? So how many examples do you have in some sense? How big is the dimension of your data versus the number of samples?
This is, I think we took a subset. I think it's 10,000 examples. And the dimension of the data is 28 squares, which is, I think, 784.
Okay, so roughly the same.
No, the number of samples is significantly larger, like 10 times as big. Is the dimension. Yeah.
Sir, what is the dotted blue line?
Which one?
The one that's just above the Laplace kernel.
This is a prediction of this kernel machine which fits the data exactly, the training data exactly. So that has 0 square loss. So you cannot fit it any better than that in a computer. So you can see that there is very little, if any, overfitting here, which is quite remarkable because you would think that. And now, why is this a problem for this kind of WYSIWYG bounds? Because, well, if you think about it, well, your empirical loss is 0, right? So if you want to have a bound, you only have this term in that bound. But now you know that this term has to be smaller than 0.9, because if it's bigger than 0.9, that's my bound is just saying that I'm doing as well as a random prediction, which is not an extremely useful bound. If it's smaller than 0.7, this is saying that this is wrong, right? This cannot be possibly true. So this whole thing has to be between 0.7 and 0.9 for this bound to make any sense, to be of any use. And yeah, you know, this is just like not going to happen because the constants are never exact. How would it like figure out to be like so precisely that it has to be between 0.7 and 0.9 and so on? So in fact, there was some recent work where they showed that in some cases, no such bound exists. So that shows that kind of WYSIWYG type of analysis really doesn't work. Yeah.
So in this case, the C of n is no longer just the capacity of the architecture, right, the model, because otherwise that would be constant regardless of the problem you're studying, right? In some sense, are we now thinking about capacity here in terms of an effective capacity of the model rather than a...
Yeah, it doesn't really matter. You can even make it data dependent. You still have the same problem because you can make it very flexible, but as long as the bound is still of the same form, how can you get rid of the, right? Imagine like I have a constant 2 in front of it, right? Constant 2 will break this because if this is between 0.7 and 0.9, twice that is not, or 1/2 of that is not. So like you cannot allow any slack in the thing, and you just don't have anything like that. Yeah.
Is it easy to say what the assumptions are that went into that WYSIWYG bound?
Went into what? I'm sorry.
Is it easy to say what the assumptions are in deriving that bound?
There are many bounds of this form. I'm just saying that none of,
right. But supposedly
effectively none of them will have.
Supposedly it comes from somewhere.
You would need an amazing bound which has like that exact constant and doesn't have any log terms and doesn't have like any, like we just don't have anything, and it's sort of not reasonable to even think that such a thing would exist. Okay, this is not a proof that it cannot exist, but these papers actually do prove that it cannot exist in some cases. I'm just saying it's like, it would take a miracle for it to exist. Yeah, you know, maybe we believe in miracles now, but we ask ChatGPT and it shows us how to make the bound. Yeah.
The event must have some interpretation as a variance in some central limit theorem, right?
It's some sort of bound on the variance.
Right, because it's the next deviation of, right, it's the, how do you call it, fluctuations, right? Besides the mean. So what are you saying is that somehow once you inject this noise, then the variation must be infinite or something like that?
I'm just saying that if you look at this bound, like look, sorry.
I mean, I think of it as a fluctuation bound, right? So there's probably some central limit theorem, and this thing is a variance, and then there's some.
Yeah, you're quite right. So this is kind of like expected value, and this is kind of a variance. But what I'm saying, like, if this is the expected value of this, but this is no longer expected value because it just becomes 0. So how can variance also take care of the expected value? Right? This side has expected value. This side doesn't. It's 0. I mean, this term. So how can variance also incorporate the expected value in it? That just kind of sounds strange.
So what you're saying is that the law of large numbers is broken.
It just doesn't apply, right? Like the law of, there is no like you cannot take uniform law of large numbers when you say over all functions, because for any data, there is some function which fits the data, right? There is no law of large numbers. So your expected value, your empirical loss is always 0, no matter how many data points you have, right? This has very similar effect. Yeah.
I think to that point, the difference is that your dimension is changing in some sense. I think you're thinking about these regimes, you need the D to grow with the N, and therefore you're not in this regime of law of large numbers because you're not fixing the distribution, you're just growing the number of samples. You're also changing the distribution essentially by considering a sequence of distributions of changing dimension, and that's where you get this phenomenon. So that's, I think, why the law of large numbers doesn't necessarily apply in this situation.
Yeah. No, it's, if you think about it, the number of parameters in this thing, right, it's much larger than so the dimension is too high for the law of large numbers somehow to apply, right? If you think very roughly about, like, okay, you have 1.5 million parameters, but only like 50,000 data points, huh? Yeah, this is just not a setting when the law of large numbers would help you somehow. The law of large numbers help you in low dimension. In high dimension, this type of law of large numbers at least doesn't work. But let's see. So that's basically, so that's kind of broken, right? So now we have a very interesting phenomenon, right? On one side, we observe that in practice, it seems to work just fine. But in this type of bound, like this WYSIWYG type of analysis, clearly cannot, you know, if you think about history of science, there have been many things, like when you have temperature, right? And then they have, what's called? Caloric. And they explain, okay, temperature is how much of that liquid is in some sort of thing. Well, it was a good theory. It explained many things, but we sort of thought that it doesn't really explain many things that were observed, right? So people got rid of caloric as a theory. So this is kind of maybe of this form. It's not necessarily, well, okay, caloric, you can say there is nothing like that. This is mathematically, of course, correct, these bounds. They just don't apply in this setting. They would apply if you have a very limited set of functions in a lot of data, right? So it's not that they're useless, but they just don't apply in this type of setting. Okay, so let me point out now, like there are actually some analyses which work in this setting. In one remarkable analysis is the one nearest neighbor predictor. Now, if you think about, well, what is one nearest neighbor, right? You have a bunch of points. Given a new point, you select the point which is closest to your new point, and just assign that label to the point, right? One nearest neighbor. That's sort of trivially an interpolating predictor. Because, of course, if you give it the point itself, the closest point would be, assuming the point don't repeat. That would be the point. So the loss of such a thing, empirical loss, will be always 0. But we have a bound for it. It's a sort of classical cover and heart analysis. And this is kind of a nice bound that one nearest neighbor predictor is at least as good, well, at least given enough data, is as good essentially as twice the loss of the optimal predictor, which is not too bad. Maybe not too good, not too bad. Now, there is something even more interesting here, and I'm not going to discuss the details of this, but this was actually the first I think, observation of this type. There is something called a Hilbert regression. Well, they call it Hilbert regression scheme, and I can, in fact, write down for you what it is. It's a form of an Watson predictor. It's really simple. So take your kernel. So just take the function k of xi to be 1 over x minus xi, maybe to some power alpha, to some positive power. Now you can construct the following. Just take f of x to be sum, let me see, k of xi times yi over, like I being my data, so xi, yi are my pairs of data points, and I think I need to normalize it by some k of xi. Okay, it's just this. Now, if you think about it, this actually is called something Shepard's interpolation. And in fact, it was this guy Shepard's math thesis, apparently at MIT, like 68. He proposed this scheme for interpolation. He didn't prove anything about this. Oh, no, nothing in this case. But Devroy, Yorfe, and Kruzak actually showed that this interpolation has this remarkable property. So let me first point out what happens, right? So what happens when x becomes close to xi, right? This thing goes to infinity. So this term becomes dominant. So that's the term as x tends to xi, the corresponding term becomes dominant. So you can kind of get rid of all the other terms. And now you have the same term at the bottom. So they cancel out, and you just get yi. So it's easy to see that actually it's a proper interpolating predictor. It's continuous, easy to check, but not differentiable, of course, because of the singularity. Turns out that this thing is consistent for some choice of alpha, like I think d over 2 and d is a dimension. That's what they showed. And this is pretty remarkable, right? Because it looks pretty crazy that something like that can. What do I mean by consistent? That at least given enough data, it's close to the optimal predictor for regression specifically. So you can, in principle, have something which interpolates the data and yet has some sort of nice statistical property. Okay, any questions about this? So the kind of amusing thing is like, this is a pretty obscure paper. Sorry, I shouldn't say that, but it is. Like they didn't definitely when they wrote it, it's kind of clear they thought this is some sort of mathematical.
Is it related to barycentric interpolation or rational function?
I don't know about rational function, but it's actually related to various. Actually, let me show you the next slide, because maybe that's what you have in mind. Yeah?
You can never have it be closed in the subnorm, right? It can only be in some kind of average sense.
Yes, only in average sense. So there is no way this can be closed in the subnorm, because it's obviously going to fit every noisy point. So something like this can actually predict accurately. It's pretty remarkable, right? Because you would think like, okay, this is crazy. And the kind of amazing thing is that it looks like it actually explains a lot of what's going on with neural networks, or at least some of what's going on with neural networks, which is, yeah, any other questions? Let me point, yeah.
Just in the example you had of switching a certain percentage of points, the k nearest neighbor approach, as k gets reasonably large, would work.
Oh, yeah, of course. Why? But k nearest neighbor is not an interpolator, right? K nearest neighbor actually is WYSIWYG.
Right, but this is sort of a limit of k nearest neighbor in a certain sense. Right?
It's a very special, you can think of this as the nearest neighbor, but with a very special weighting function, right? The weighting function is singular. Yeah, so you can view it as a nearest neighbor scheme. Yeah, let me actually, I think this, you can think about, okay, I kind of like the simplicial interpolation. I don't know whether it relates to barycentric interpolation for rational function, but it's like you can have the following scheme, very simple interpolation scheme. So what you do, you have your data point, you just triangulate it. Let's not worry about how hard it is and so on. And now I have a function, so this is my training data. Now I have a function on these triangles, right? And I just do linear interpolation on each piece. So I have the 3 values, right? There is a unique linear function which has the 3 values, so I have something like this. And now if I want, this is for classification now. Now I just, to classify, you just threshold it. Like you think this is 0, this is 1, so you threshold it 0.5. And it becomes quite interesting because, well, what is happening now is that now I have a predictor which is based on this interpolation. It's kind of triangulation. And like if you think about what is happening here, suppose this, like let's think about this point as being noise, right? So suppose all points should be red here, but just by accident I got this red point, and that's noise. Now let's see how much price do I pay for interpolating this point. Well, if it's one nearest neighbor, you can see there are 3 points, and I will pay 1/3. The price is 1/3, right? Because that will get classified. This is the points which are closer to that point than to that one, so I'll classify all of this as blue, and I'll pay 1/3. Now, with simplicial interpolation, I pay the area of this little triangle, and it has like it's the size, the base is 1/2, the height is 1/2, so it's 1/4. So you can see I pay less with simplicial interpolation. Now let's see what happens if my dimension is higher. If my dimension instead of this is a simplex, right, in dimension d, this I'm going to pay 1/d, or 1/d plus 1, I guess. There are d plus 1 vertices. Now, if I have this thing in dimension d, I'm going to pay 1/2 to the d. Because every dimension is 1d, so there are there are d dimensions, so it's 2 to the d. Yes?
I must have missed the definition of simplicial interpolation. Did you have that on the last slide?
It's simply the following. So if I have a simplex, and I have values on the simplex, there is a unique linear function. So if I have 3 points, right, there is a unique plate which goes through the 3 points. That's just my interpolating function. So on each simplex, so I'm cutting this into 4 simplexes like this. And on each one, I'm doing separately.
So is this a 3 simplex that I'm looking at right now?
You are thinking of, you should think about this as a 3-dimensional picture. Well, it's 2 plus 1 dimension. My axes are in 1 dimension, and this color indicates plus or minus 1. So now the simplex is going to be like this. It's going to be, well, the simplex is actually 2-dimensional, but the function is going to be 3, right? So you have 1 here, 0 and 0 here, and it's going to be like that. Is it okay? It's still confusing.
I'll try to follow along.
So along any edge, everything that's halfway towards blue would be classified as blue, right?
Yeah, so, okay. Well, maybe let me, so I have a linear function, which is 0 here, and 1 is here. Now, where is it going to be 1/2? Well, it's going to be 1/2 exactly half the way here. And when it's above 1/2, I'll classify as blue. When it's below 1/2, I classify as red. So that's the kind of picture that I have. And I do this separately for every triangle. Now I can do this in any number of dimensions. It's exactly the same procedure. And so the interesting thing here is that the area becomes very small. That the area which is the cost that I pay for the misclassification price becomes very small when my dimension increases, because it's something like 1 to 2 to the d. Here it's only 1/d. So you can see in high dimension, I can tolerate quite a few errors, and I still only pay 1/2 to the d, which is very little. So yeah, it's not going to be completely consistent, but I will just pay a very small price. Now, if your dimension is like 1,000, which is, like something like that for those images. You pay something like, okay, 1/2 to the 1,000 is nothing. It's 0. So in any case, you can prove something about this. You can turn this. This is basically a theorem. But that's maybe a phenomenon that in high dimension, it's somehow easier to do the things. Because you can do things which really, like in one dimension, if you do that, it doesn't quite give you any benefit. But in high dimension, you do something very simple like that. You already see that there is why is it, like, you can kind of think maybe in a different way what this thing does. Around every like noisy point, it creates this little tent. But the volume of the tent in high dimension is very small. It's like very, very needle-like, which is sort of something like this, right? It creates a spike, but the spike is so localized that you don't pay much for it. Like you can fit the data exactly and not pay somehow the price for overfitting, or pay very little price. Overfitting for cheap. In any case, what happens now with so these are all very different methods, right? There's not neural networks and nothing like is being used in practice, except maybe for one nearest neighbor. But what happens with real networks is actually quite interesting. And you can summarize this in this, what we call the double descent curve. You have, so let's think about the x-axis as how many parameters you have. Okay, so here the models are very big, and here they're quite small. And on the y-axis, you have some sort of loss, okay? And if you look at the training loss, right, as your model becomes bigger and bigger, just let's think that we fit them as well as possible. As your model becomes bigger, your training loss is decreasing, right? And when the model becomes sufficiently large to fit the data exactly, which we call the interpolation threshold, it becomes 0, right? And from this point on, it is 0. What is interesting is that you get this U-shaped curve in this classical regime. So this is underfitting. This is somehow perfect fit, and this is overfitting, exactly what Wapnick had. But something quite interesting happened after you pass the threshold, because after you have enough parameters to fully fit your data, more parameters is helping you. And the more parameters you have, generally, this is, okay, again, I have to add a bunch of caveats, but sort of generally, bigger models work better. So that's very consistent with what we observe in practice for most of these models. Any questions about this? Because I'll give you an example of something like that happening in a second. Yeah?
If I understood correctly, this interpolation method would have a fixed number of parameters fixed by the data, if I understand correctly.
So here you kind of think of data being fixed and model kind of just growing. Like you do small neural networks, then bigger neural networks, then even bigger, and so on.
For example, in the simplicial interpolation, can you do that? Or because the data are fixed, then in that case, it's fixed the number of parameters?
So simplicial interpolation of a different kind, because you don't have there are no parameters there, right? It's some sort of non-parametric thing. So you can always fit with simplicial interpolation. It's a lot like one nearest neighbor, right? Like one nearest neighbor, it will always fit your data perfectly.
Yeah. So my question is that could we, given that it's just one case, would it make sense to put this interpolation somewhere there on the x-axis?
For this method, there is no interpolation threshold, right? Because they will always interpolate. Interpolation threshold only makes sense when you're changing somehow the capacity of the model. Those models always have infinite capacity. They'll just fit whatever you give them.
If I may bring in a Zoom questioner, you see the hand has gone up. Wait, I'm clicking on this. Yep. Okay. Good. Go ahead, Victor.
So the picture you described was specifically in the context of classification where your goal is to maximize the accuracy. But what if you wanted the probability? So you wanted to...
Oh. What happened?
Just raise your hand.
That question was too dangerous. I'm sorry. Yeah. Let me answer at least the first part of the question. This is not just for classification. You get exactly the same picture for regression. So even though I sort of emphasize classification. And in fact, the result of de Vroy was for regression. This one. Okay. Let me. Let me now actually point out let me give you an example of this neural network. It's a super simple neural network, but okay. Just take the following neural network. Okay, you take a linear, it's a two-layer neural network, right? You take a linear combination of ReLU. So ReLU is just max of x0, right? It's this function, the hinge function. And you take a linear combination. And I'm just going to choose B and C randomly. Okay, I'm fixing the first layer. I'm only going to train this alphas, which is the second layer of the neural network, and I'm going to vary the number of parameters D. Okay. Very simple mathematical setup. The cool thing about it, if you fix the first layer, you only choose alphas, and if you want to fit the data, this is using the square loss. This is the same as minimizing the square loss, and that just becomes a linear problem. So I can do it exactly. I don't have to do gradient descent. I solve a linear system of equations. Now I'm just going to do it for some points. These are just some points in one dimension. Let's just see what this curve does, sort of to demonstrate this effect. So, okay, these are 3 neurons. Neurons in this case correspond to this D is a number of neurons. You know, that's the terminology. So you can see I have some points here, and I find some piecewise linear function. Well, it's a sum of ReLUs is always piecewise linear. Okay, it's a reasonable fit. You can say, okay, pretty good. Definitely sort of WYSIWYG. Okay, I didn't tell you what the distribution was, but you can see I'm not fitting data exactly. Probably will be okay. Now let's increase the number of neurons, and I'll increase them to 30. What is going to happen if I have 30 neurons? Well, you can, okay, it's 30 neurons, definitely enough to fit this data exactly. And it's probably going to do some sort of fairly crazy stuff, which is exactly what it does, right? It's sort of classically, if you think about interpolation, polynomial interpolation or something like that, you may get something like that, some sort of oscillatory behavior. Yeah, you can see. And now let me increase the number of neurons one more time to 3,000. Okay, now it's way overparameterized. This is just barely overparameterized. What is going to happen when I do 3,000? Yeah?
It's going to smooth out, it'll still...
It's going to smooth out, right? That's actually the law of large numbers, but it's very different from that one. You're going to get this pretty nice curve, and now you can say, well, this is clearly bad. Which one is better, this or that? Well, kind of hard to judge, but they're both pretty sensible, right? Again, this is not obviously a mathematical statement. This is, again, some sort of reasonable thing. But so you can see that you cannot, you can no longer see that it's piecewise linear, even because with 3,000 pieces, this is way too much to see. So it looks smooth. And of course, in the limit, it's actually going to, I think it's a cubic spline in the limit. Yes, the number of neurons goes to infinity. So you can see you kind of have on one side, you have this kind of nice, fairly nice parametric fit. In the middle, you get this crazy overfitting. And on the right side, you get some sort of nice non-parametric fit. So you get this span of these possibilities. Okay, I'm not going to talk more about, and in fact, I think I'm getting close to the end of this half. There are mathematical now analysis of this benign overfitting kind of phenomenon. And if you're interested, I'm not going to discuss like how to analyze, at least for linear systems now we understand. Actually, remarkably, this is even a thing for very simple like linear predictor for linear regression and so on. So yeah, you know, this is year 2024, and we're writing papers about linear regression. Like, didn't Gauss invent that? He did, right? In any case, so there is two recent reviewed papers, one by Peter Bartlett, Andrea Montanari, and Sasha Rachlin. I also wrote one. Okay. Now, let me maybe very quickly say something about, so this actually suggests that like if finite networks are good, right, and increasing the width of this network helps, right? I kind of claim that, okay, bigger networks are better. And that's what we see in practice too. Wouldn't like infinite networks be best? Okay, well, infinite networks are really difficult because, well, how do you implement them? Turns out that you can. This is actually pretty remarkable because there is some sort of law of large numbers. There is some sort of mathematical structure to the things. And in fact, there is this beautiful kind of classical theory based on reproducing kernel Hilbert spaces, which actually give you infinite networks. And starting with Aron, I guess in 1950, who sort of introduced the framework, and you know, more recently like splines, and then kernel machines. And very recently, it has been shown, and in particular this work by Jacob, Gabriel, and Hogler from 2018, that under certain conditions, very wide neural networks are in fact kernel machines. Let me just define kernel machines right now, and then I'll continue next time. What is a kernel machine? Well, imagine I have some rich class of functions, H, like maybe like think about like a Sobolev space of sufficient smoothness or something like that. And well, okay, technically you want it to be an RKHS, so if you're familiar with that notion, it's a space where function evaluations are bounded. But you can think of maybe Sobolev space or something similar to that. It needs to be a Hilbert space. Now, I'm choosing a function such that f of x minus yi, the sum, which is my empirical loss, is minimized plus this norm. So I kind of trying to control the norm of the function and fit to the data. It's a pretty classical setup with splines actually defined the same way. And here is the key algorithmic insight, and this is amazing because it's somehow just like magically gives you this, is that a representer theorem gives you some, well, first there is some kernel function, which is just a function of two variables, so that, so this is an infinite dimensional problem potentially, right? Because I need to optimize over some infinite dimensional functional space. But amazingly, there is a corresponding kernel, and you have the representer theorem, which says that the solution of this is simply a linear combination of kernel over your data points. Now this is why this is such a striking thing, is because this allows you to reduce from an infinite dimensional to finite dimensional. This you cannot do in a computer, but this you can. So this becomes a very practical thing as long as you know the kernel. And in fact, if you know the kernel, you just compute the kernel matrix, which is my matrix on the kernel over pairs of data points. This is n by n matrix. And you simply do the inversion of that matrix. That's your solution. So you just need to solve a system of linear equations. Very nice. You can do it even when the systems are fairly large. Yeah?
I think I'm not following. Where's little k defined?
I have not. Let me point out. So in general, it's hard to find k for the h, but you can kind of invert it and say like, do I know some k's for which it works? And the answer is yes, and they're like Gaussian kernel. So you can take this to be Gaussian kernel. Actually, in practice, it looks like Laplace kernel, which is Gaussian without a square. It seems to work better in most cases, or at least as well. It has some advantages.
What is that k does not depend on your problem? It's just setting up the structure of the Hilbert.
You just said, so you choose this k, and choosing a k also gives you h. So you never, so like the way I set it up here is actually not really a useful practically way to set it up, because in practice what you do, you choose this, you say, okay, I like Gaussian kernels because, I can compute them. And now I just solve this system, and the solution has this form. So everything is very explicit. Like you can just write it down, plug it in the computer and get a solution. Okay, any questions? Maybe I should probably stop here, but yeah, I'll continue next time, and we'll get to emergence, I promise.